Hello everyone. So today we are going to discuss about our next topic, that is salting out and hydrophobic interaction chromatography. Okay. So as you remember that same flow diagram where we explain the different steps of protein purification. So salting out is also a step of protein capturing in our purification, like flow chart. So as you remember, uh, we discussed IMAC, or immobilized metal affinity chromatography, or nickel NTA chromatography. That chromatography was for the capturing of recombinant protein that already have a hexahistidine tag. Okay, so we can capture recombinant protein with hexahistidine tag using IMAC. But for protein that is from natural source, okay, which don't have any recombinant tag or affinity tag on it, so how we are going to capture those protein in our purification steps? Okay, so for that, what we do normally, we do a ammonium sulfate precipitation, okay, or it's called salting out. So remember, this is a capturing step. Okay, so what exactly mean by salting out? So there is another term, it's called salting in. Okay, so the solubility of a protein depends on the ionic strength and presence of different ions and salt in the solution. Okay, so if you start increasing concentration of salt in a protein solution starting from zero, what would be the effect on solubility? So initially, if there is no salt, okay, then protein would be less soluble. Okay, and there would be aggregation formation. So if you keep increasing concentration of salt slowly, then you will see that solubility of the protein increases. Okay, so up to a certain time, so that part is called salting in. That means it's increasing the solubility of the protein, it increasing solubility of the protein with addition of salt. So salting in happens in presence of very low concentration of salt. Okay, then after it's reached a certain, like highest solubility stage, if you keep increasing the salt, okay, so then it will then decrease the solubility of the protein. Okay, and that means it will induce protein aggregation and precipitation. That means it will remove protein from the solution. So that's why this process is called salting out. Okay, so salting in happens when salt concentration is low. Salting out happens when the salt concentration is really high. Here, so you see here, salt at low concentration helping to solubilize protein. At high concentration, it's removing the protein from the solution. Okay, or precipitating the protein. So what is happening there? So you see in this picture, as you can see, the proteins, so they are in a aggregate form. Okay, and salts are around. So if you keep adding salt, then those salt ion, cations and anions, they will start interacting with the individual protein molecule. Okay, and because of the charge repulsion, it will prevent aggregation formation. Okay, and it makes the protein more soluble. So in this stage, you see the each and every individual protein molecule, they are interacting with different salt, and the aggregation is broken down. Like now each and individual molecules are in soluble stage. Now if you keep increasing the salt again, so what would happen? Again aggregation would form at high salt concentration. Okay, and it will precipitate the protein, and that phenomena is called salting out. So salting in when small amount of salt or low concentration of salt increasing solubility of a protein. High concentration of salt when decreasing solubility, it will called salting out. So let's uh, see why this kind of uh, incident happens. Okay, why salting in and salting? You understood already what is salting in. So when the low concentration of salt interact with the surface charge of a protein and therefore prevent intermolecular interaction, then protein become more soluble. So that is the salting in. So what happens to salting out? So if you see, if this is a protein, you'll find there are some charge residue that is in surface of the protein. There would be some residue which are hydrophobic. Okay. So in general, protein has hydrophobic surface patches. Okay. That means a region of the surface where a few number of hydrophobic residues are concentrated there. So it acts like a patch of hydrophobic uh, residue. Okay. So protein surface looks like that. So if it is a globular protein, means water soluble protein, then there will be more charge residue compared to the hydrophobic patches. If it is a membrane protein, then there will be more these hydrophobic patches than the charge residue. Okay. Now, typically in a hydrophobic patch, there would be residue like phenylalanine, tyrosine, tryptophan, leucine, methionine, valine, all these things. Okay. So what happens to the water around the protein? So when a molecule is soluble, when all the water molecule interact with the molecule, like the molecule of our interest, and make it soluble to the water. Okay. So if there is a hydrophobic patch, so the water there, because this is a hydrophobic, because they have phobia for water. So similarly, water also has phobia for that hydrophobic residues. Okay. So around that hydrophobic patch, the water would be highly ordered and kind of a frozen condition. Okay. There is not much movement going on here. And because of this water shielding, okay, two protein molecule cannot interact through this hydrophobic patch. Okay. So this is the bulk water. You see, these are random bulk water, and these are the ordered water around a hydrophobic patch. So if you add a salt that can pull out all these water molecules around the hydrophobic patch, it will enhance the ability of two protein molecule to interact through intermolecular hydrophobic interaction, and then it will promote aggregation. So that is the phenomena is called salting out. So you see here, protein molecules, they are all surrounded by water and salts, low concentration of salt. Okay. When you add a high concentration of neutral salt, then what it would do, it will take out all the structured water from the surface of the protein molecule. Okay. By doing so, it will uh, make the hydrophobic patches of the protein molecule accessible to the other molecules, and then enhance the intermolecular hydrophobic interaction that will cause protein aggregation, and then it will precipitate. So the log solubility of the protein equal to A minus M salt concentration. So A is a constant that depends on temperature and pH, and M is a constant that is independent of temperature and pH. So for a particular protein, we can calculate A and M experimentally. Okay. And then finally, we can use this parameter for determining the solubility of that protein uh, for other purpose. So now we already understood what is salting out. So it's high concentration of salt that can precipitate protein or create aggregated protein form that could be less soluble in the solution. So is all the salts are equally good to do salting out? So for that, we have to look at this uh, series. It's called Hofmeister series. Okay. So here we have a list of anions depending on their lipotropic effect. Okay, means how much interaction it can cause with the how much solubilize it can make the protein. Okay, in presence of these anions. So you can see the anions which are more complex and multiple negative charge, they have better lipotropic effect, means it will increase surface tension, reduce solubility of the protein, or cause salting out, whereas protein denaturation is low in presence of this salt. This salt don't denature the protein, and stability of the protein is quite high in presence of this salt. So that means this salt can precipitate but don't denature the protein. Whereas the right side of this series, there are ions which are less complex and have single anionic charge. So these are this salt, presence of this salt would reduce the surface tension. It will increase the solubility of the protein, that like salting in kind of thing. Okay, and it might denature the protein as well as destabilize the protein. So for salting out, choice of our salt or anion would be on the left side of this Hofmeister series. So as we describe the lyotropic series, so there is another thing is called chaotropic agents. Okay, so what is lyotropic agents? Which solubilize protein and don't denature protein. It is not harmful for the protein structure. What is chaotropic protein agents? These are the salt that denature protein. Okay, so we don't want to use any chaotropic agent for salting out. Okay, because that denature the protein. It disrupt hydrogen bonding and uh, make it destabilize the protein structure, destabilize. So this is a complete list of cationic and anionic ions. So you can see for salting out ammonium, sulfate or carbonate, cesium, these are the better candidate, whereas lithium, isocyanate or chlorate, these are not that good for salting out, but low concentration of these salt or divalent cations, they can enhance the solubility, means it can promote salting in. Okay, so similarly, so we understood what is the effect of salt on the solubility of the protein. So now we want to discuss what is the effect of pH on the solubility of a protein. So as we all know that each and every amino acid has a isoelectric point, that is the pH, where the net charge of the amino acid would be 0. Similarly, proteins, they are made up of amino acid, so definitely protein would have a isoelectric point. Okay, so the solubility of a protein, as you can see from this graph, is lowest at its isoelectric point. Okay, so it's a reverse bell shaped curve, and you go away from the isoelectric point in either direction, you'll see the solubility increasing. So why it's so? So you can see normally the protein molecules, they have a net charge. So if it is lower, if the pH is lower than isoelectric point, then it will have a positive charge, net positive charge. If it is higher than the isoelectric point, then there will be net negative charge. And we all know like same charge repel each other. Okay, so if the pH is higher than isoelectric point, protein would have net negative charge, and two molecules of same protein would have same amount of negative charge and negative repulsion. Because of this negative repulsion, they would not form any aggregate. Okay, and stay in the solution. Same thing is true for the pH which is lower than isoelectric point. So the protein would have net positive charge, and because of positive repulsion, the protein would be in the solution. However, if the pH is exactly same as isoelectric point, then the protein would have net charge 0. That means there would be no charge repulsion. Instead, what would be there? Hydrophobic and rest of the other interaction, and that would form aggregate, and then protein would get precipitate. So our aim would be to keep the protein away from isoelectric point. Okay, that would make the protein more soluble. So using salting out, we can purify or extract protein. Like if we add a particular concentration of ammonium sulfate salt, it will precipitate protein of our interest, and we can resolubilize that protein by removing the ammonium sulfate salt. And another thing we learned from this last part is presence of high concentration of salt enhance hydrophobic interaction. Okay, so how we can use these two information for further purification of a particular protein. Okay, so for that, what we are going to discuss, we're going to discuss about hydrophobic interaction chromatography. So in IMAC, the immobilized metal affinity chromatography, the interaction between protein and the matrix was by charge interaction, or it was a proper affinity, means protein ligand interaction. Okay, and that was between a hexahistidine tag and nickel ion. Okay, so in IMAC, protein get purified based on the presence or absence of the histidine tag. But in case of hydrophobic interaction chromatography, you don't need any specific tag here. Okay, but when you apply the protein mixture into the column, protein would get separated based on their surface hydrophobicity. Okay, so hydrophobic interaction chromatography use surface hydrophobicity of the protein to separate different protein from each other. Clear? And what is happening inside the matrix? So the matrix is a hydrophobic, like, ligand. It has a hydrophobic ligand. Okay, so based on the hydrophobicity of the protein, it will either strongly bind to the matrix or weakly bind to the matrix. And then if it is strongly bound, it will retain the protein for longer time. So it would get separated from the weakly bound protein, because that would get released by the matrix at the initial stage of the purification. So you can see here, this is the solid support of the matrix, or the bead, saccharose, whatever, like we know, like, inert carbohydrate polymer, and there would be a spacer arm, and then the hydrophobic ligand. So hydrophobic ligands, they are again surrounded by the ordered water. Just we explained in our last few slide back. Similarly, the hydrophobic part of the protein would be also surrounded by the structured water. So if we apply this protein into the matrix, then because of the hydrophobic interaction, the protein would bind to the hydrophobic ligand, and the structured water would be removed. So to remove this structured water, we have to have high concentration of salt. So as we already understood, like why high concentration of salt favor hydrophobic interaction, because it remove the structured water around the hydrophobic patches. So in presence of high concentration of salt, if we apply the protein to a hydrophobic column, then it will bind to the column based on the strength of the hydrophobic or, like, the extent of hydrophobic patches that the protein has. Okay, or surface hydrophobicity. So protein might get purified based on the surface hydrophobicity. So these are the different ligand, hydrophobic ligand, which are possible or which we can use as hydrophobic matrix. Okay, we can have a phenyl group, we can have butyl group, we can have octyl group, okay, isopropyl group, all this group we can use as hydrophobic ligand. So you can see these are like hydrocarbons. So they would have hydrophobicity, and they can interact with the hydrophobic part of the protein. And the question is, how would we know which matrix would work best for our protein of interest? So there is no hard and fast thumb rule that okay, this matrix would work here. So if it is more hydrophobic, then stronger binder would. So this is, if the protein has more hydrophobic patches, and if you are using a very strong hydrophobic column like octyl or something, then it will bind so tightly to the column that it will not like get out of the column ever, okay, until unless you denature the protein. Whereas if it is very weak binding, and if you are using a weak matrix, then it might not bind. Okay, so that's why a normal rule of thumb is first time we screen for all the columns. So you see these are the different columns that you can purchase from commercial source, and you have to give one trial for each and every column, and whichever giving you best result, you can use that column for further optimization. Okay, so when we talk about protein purification, we sometimes call it FPLC. Okay, so FPLC system that we use for different column chromatography. Okay, so FPLC system, what it is nothing but two pumps, okay, that connected with some different accessories. Okay, so you can see there would be a buffer A and buffer B. These are the inlets. They will be connected to the pump, and that pump would pump that buffer A and B based on your requirement to the column. Okay, and it can also, this is sample injected. So a lot of APL system might have or might not have this sample injected. So you can automatically inject your sample also, and automatically collect the eluent coming from your column. Okay, it can automatically collect the fractions. So this is, so you can see like a PLC system is nothing but to pump and a monitoring system, like there is a UV detector. So as you know, like protein absorb at 280. So if we keep recording the UV absorbance at 280 for the like liquid that is coming from the column, then we might get a peak of the protein from where we can identify where exactly the protein can be found in which fraction. Okay, so this is a PLC system. So this is nothing but two pumps, one detector, fraction collector, and column whatever you want to put. So if you want to put a nickel column, you can run nickel column. If you want to put a hydrophobic column, you can tag the hydrophobic column here. Okay, so the best thing about this APLC system is you can automatically create a gradient of buffer A and buffer B. So you don't have to do isocratic elution. You can do a gradient elution, and the gradient would be made by the machine by pumping buffer A and buffer B in defined amount continuously in a linear gradient. Okay. So what are the steps of hydrophobic interaction chromatography? So any column that we already mentioned, they would have these steps that are common. Okay, first step would be equilibration of the column. Okay, so we have to equilibrate the column in the buffer in which we are going to apply our protein into the column. That means in the binding buffer. So what we have mentioned, that the hydrophobic interaction enhance in presence of high concentration of salt, ammonium sulfate. Okay, so binding buffer would be maybe 20 millimolar Cris HCl, pH 8. That changes with your preference. Okay, this is not hard and fast like you have to keep Cris buffer or like pH 8 or the concentration. Depending on your protein or requirement, you can change the buffer and pH. Okay, but the thing you have to keep is 1 to 1.5 molar ammonium sulfate salt there. Okay, so that salt would enhance the hydrophobic interaction. So see, then we have to apply the protein in the binding stage when the protein is with 1 to 1.5 molar ammonium sulfate salt. So that's why we are discussing the salting out and hydrophobic interaction chromatography together, because the obvious step after the salting out would be hydrophobic interaction chromatography. Why? Because after salting out, your protein is already in high ammonium sulfate salt, isn't it? So if the protein is already high in the presence of high salt, then you don't have to do any like in a specific step before you can load that protein into your hydrophobic interaction column, isn't it? So in the binding buffer would be in presence of high ammonium sulfate, and then you can wash the column with the same buffer A, and then elute the protein with a gradient of buffer A, which is high salt, and buffer B, which is low salt. So sometimes we use 10% glycerol in buffer B, because glycerol prevent hydrophobic interaction. As high concentration of ammonium sulfate, what we understood that high concentration of ammonium sulfate increase the hydrophobic interaction. Glycerol reduce hydrophobic interaction. So in the elution step, the buffer what we are applying, if we increase the concentration of glycerol slowly, then it would prevent hydrophobic interaction and bring the protein out of the column. Okay. So if we check the structure of glycerol, you see this is an amphiphilic molecule. Amphiphilic molecule means it has some hydrophobic part and a hydrophilic part. Okay. So it can interact with the hydrophobic patch of the protein, and then it can solubilize the protein by forming hydrogen bonding with the water. Okay. So with this hydrocarbon part, it interact with the protein, and with these OH groups, it can form hydrogen bonding to the water, and that's how glycerol stabilize or solubilize the protein. Okay. So we say, like, glycerol, it prevent intermolecular hydrophobic interaction and enhance or stabilize intramolecular hydrophobic interaction. Okay, by forming or solubilizing the protein through its OH group. So in this diagram, you can see, so at high salt, when we apply protein, so you see there are three kind of protein. Some protein which has high surface hydrophobicity, some are medium amount of surface hydrophobicity, and some don't have any hydrophobicity, surface hydrophobicity. So in the binding stage, even if there is high concentration of salt, if the protein don't have any hydrophobic patch, enough hydrophobic patch, it would not bind. It will flow through in the binding stage. Rest of the protein, based on the amount of surface hydrophobicity it has, it will bind in different strength to the matrix. Then you start eluting the protein with gradient of salt and glycerol. So salt would reduce slowly, glycerol would increase slowly. So after a certain salt concentration reduced at the lower salt, the protein which has less hydrophobic surface patches or surface hydrophobicity, they would be removed, because they have weaker interaction with the matrix, and the protein of your interest may be whichever it is. If it has stronger interaction, it will be eluted at the end. If your protein of interest is the medium one, you get separated from the protein number, the protein which don't have any hydrophobic patch, and protein which has very strong hydrophobic interaction. So it would get, so whichever it is your protein of interest, you can get separated it from the pool of the protein. Okay. So if the protein of interest don't have any surface hydrophobic patch, then can you use hydrophobic interaction chromatography for that protein? You can. But in that case, you have to run a column in flow through mode. So I'll explain a little bit what is flow through mode in our next section. Okay. So all these affinity column you can run in two different mode. One is binding and elution mode. Binding and elution mode. What is binding and elution mode? So you see, for this protein with high hydrophobicity and medium hydrophobicity, surface hydrophobicity, once you apply that protein, it will bind to the matrix, and then you have to elute it. So this mode of interaction, mode of running column is called binding and elution mode. So that would be possible when your protein binds to the matrix. Suppose you have a protein which don't bind to your matrix, and then it will come to the flow through, but rest of the protein would stay in the column. So in that sense, still you are getting purified protein, because rest of the protein what you intend to remove, that stay in the matrix, your protein of interest coming out of the column. So you got a part of purification, a partial purification, or maybe full purification. So in that case, you don't have to bind and then elute. When you apply the protein, your impurity stay in the matrix, your protein of interest coming in the flow through. So that mode of running column is called flow through mode. Okay. So whether your protein have surface hydrophobic patch or not, you can run hydrophobic interaction to purify your protein. Okay. And what are the use of hydrophobic interaction chromatography? So this is a versatile technique. Okay. You can use for capturing stage as well as intermediate stage. Okay. As well as in the polishing step. So you see, if you remember, we have discussed the product related impurities. So these are the protein or altered protein of our interest, maybe denatured or partially unfolded protein that might not have exact biological function. Okay. So those protein, they are different from the fully folded protein by their surface hydrophobicity, isn't it? If the protein get unfolded, so their surface changes, so that the surface hydrophobicity of the folded protein and partially unfolded protein would not be same. So then we can separate those unfolded protein or partial unfolded protein using a hydrophobic interaction chromatography. Okay, so that would be in the polishing step. Okay, and that we said, like, if we are using a ammonium sulfate precipitation for our capturing, then the obvious next step would be the hydrophobic interaction chromatography, because the protein is already in high ammonium sulfate. Okay, so that's why it would be advantageous if we are using ammonium sulfate precipitation as our capturing step. Sometime when we do, like, anion exchange or cation exchange, so at the end of the we have not discussed anion exchange, cation exchange, but the elution is done with higher concentration of salt, exactly opposite as hydrophobic interaction chromatography. Hydrophobic interaction chromatography, we do reducing the salt, we elute the protein. In ion exchange, we increase salt and then elute the protein. So there, after a ion exchange chromatography, the protein is already in high salt. So then we can use that eluted protein also for hydrophobic interaction chromatography. Okay. So again, we suggest the Robert K. Scoop for further reference of this chapter. Okay. Thank you.